go ahead and solve the eigenvalue problem, right? And this is what is the main interest with respect to our set of this lecture. But we have now a matrix which represents the adjacency of all the neighboring states in the United States, which was stored in this txt file. We have been able to use pandas to export that. Now that will be represented in a matrix, and we will take the eigenvalue, and as we will solve the eigenvalue problem of that matrix, and that will help us in solving how many colors, or finding how many colors that is needed to color a given map in a such a way that no adjoining states has the same color. Okay. So again, what we are going to do is we are going to take the eigenvalue of the adjacency matrix, right? So the adjacency matrix that we have is sparse because most of the states are not neighboring of the current states, right? Only 3 or 5 states will be neighboring, but if you have a United States, there are a lot of states, so many of the entries of the adjacency matrix is going to be sparse, right? So that is going to be the case here. So what we will do is we will create this adjacency matrix, and it is a sparse matrix, and you can see that we are also calling some other libraries, for example, network X as NX. So this, why? Because we want to also do some post processing after doing the eigenvalue problem, and we want to see how we can represent this as a network of graph, and how we can color each of the node of the graph, so that the results that we are getting out of the eigenvalue problem, we want to do some visual representation of those results, and that's why you see that we have called this network X as NX, right? And this will help us in essentially storing the adjacency matrix, and also doing all the important follow-up post-processing to visualize the result that we might have got, right? So now if I execute this block of code, you can see the shape of the adjacency matrix, U is 49 by 49. Now I want to make an important remark that what we have done is we have removed Alaska, Hawaii, and Virgin Islands because they are not in the mainland. They are it might not be useful to represent them because they can be isolated and they can be easily colored, right? So for convenience, we have basically taken the information of the 49 states out of all the states that are out there, and that's why the dimension of the matrix U is 49 by 49, because that will be the adjacency matrix that will help us in representing the neighboring states with each other. Okay. Now once we have do that, right, we got this matrix which has 49 by 49 entries. Now what we do is we will essentially use the numpy's command linalg.eig, and we will provide the input to the matrix, which is the adj mat, right? So adj underscore mat is the matrix, the adjacency matrix that is there. We will pass on that adjacency matrix, and we will compute the eigenvalue problem for that. So if you look into this line of code that is visible right now, which is np.linalg.eig, and in the round parenthesis we have add underscore mat. Add underscore mat is the adjacency matrix of the neighboring state. So that's what we are passing on to the function np.linalg.eig, and that will help us in computing the eigenvalues of the adjacency matrix. So let's go ahead and execute it. And if you execute this, you will get this different arrays that are there. You want to, so these are the different eigenvalues that you can see, but the important thing that you want to point out from this, which we are going to use in a a theoretical result that I will discuss in a little bit, is that the maximum value of the eigenvalue that you get out of this solving is 5.385, and the minimum value that you get out of this is minus 2.88, right? So those are the maximum and the minimum eigenvalues that you get out after solving the eigenvalue problem for adj underscore mat matrix. Now turns out there is a theorem that gives the bound for possible number of colors to map as follows, and if I have provided the link, so if you're interested in reading this link right here, this link will this reference will help you in understanding where the results are getting, but I want to basically focus on summarizing what this results test, right? So it says, the number of colors K, capital K, will be given by the equation that is listed just here, right? This equation that we have here, this max round bracket, right? And this is correlated with the maximum and minimum eigenvalues that we have, right? So using the command that is listed here, we were able to compute what is the maximum eigenvalue, which is 5.3186, what is the minimum eigenvalue, which is minus 2.888, and now using this and substituting that in the equation which defines the bound of the color that is going to be there, what we have done here, that we have used a lambda max value of 5.3186 and lambda mean value of minus 2.888, and we have substituted that on the equation that is here. And so if you see that derivation is listed here, so if you put that in the equation that is out there, you will get that the bound of k is, so k has to be less than equal to is greater than or equal to 2.84 or less than equal to 6.38. Now these are essentially float values, right? So k has to belong in the range of 2.84 comma 6.318, but the number of actual colors could be only integers. So what is the nearest integer corresponding to this float values? Those nearest integers are 3 and 6, right? So for 2.84 is close to 3 and 6.318 is close to 6. So the bound or the minimum number of colors that we will need to color this map is essentially going to be somewhere between 3 and 6. Okay, so that gives an indication how many colors that we will be needing, but that does not actually solve the overall problem, right? Now it turns out that the possible number of colors that you will need to cover an entire map without having the same color could be any of these values, 3, 4, 5 and 6, right? Now it turns out, right, that the least possible value that will be needed is 3 if the number of states are even. Now we have taken a U matrix where the number entries are 49 by 49. We have excluded some of the states in the United States, right, in order to arrive 49 by 49 matrix, and that 49 number is not an even, it's an odd. So we will need something different than 3. So the minimum one is corresponding to the even states that you have. Now, so people have worked on this problem, and they have found that, essentially if you go, the minimum possible number of colors to cover the entire map would be 4 for any possible scenarios. And if you're interested in reading about how they derived it, this is the reference that you can follow, which is from a princeton.edu website, and you can find out that the minimum number of colors that you will need to color any given world map is 4. And similarly also it turns out for the United States, that's a good representative of the complexity of this problem. You will essentially need 4 colors, right? So again, what we have been able to do using an eigenvalue problem, we have been able to find out the bound, which is the this value of 3, 4, 5 and 6. That will be the minimum color that will be needed. We know for sure that 3 will be not right because our U is 49 by 49. So any values 4, 5 and 6. And now can we try out with 4 and see whether we can color? Can we try out with 5 and see whether we can color all the maps and so on? And we will try to pick up the smallest value of k that solves the problem. Now it turns out the smallest value of k that solves the problem of interest is going to be 4 in our case, and that's why we will need 4 number of colors to color the map of United States that is out there.